And look at that. We are live. Well, if it's purely imaginary. Hey, emergency. What's going on? How's it going? I'm just doing a few things here while waiting for people to show up. Well, yeah, then we do want that. Oops. If we're just doing that, we don't really need to make this. How are you doing today? Good. Very good. Very, very good. There we go. Okay. So, quick question. Have you ever worked with packages? You've heard of packages. Yeah, okay. That's pretty much what I'm going for. I think we'll start with the GitHub page. And actually, why don't we just go ahead and say add the code command and say Here we go. So now if you say code, then you can just click that link and then get the code. Here we go. This is always the weirdest part of the stream for me, because it's kind of like, I don't know, I'm just sitting here waiting for a number of people to show up. So I mean, not that I don't like talking to just one person, but the idea is to present to anybody that wants to hear it. And so I really need to work on getting a like a about to go live thing ready, and I'll put that up like 5 minutes before I actually come on. I think that's what needs to happen. Have I ever played Crypt of the Necromancer? Yes, I have. I have that game, and it's really fun. Yeah. Necro Dancer. Yeah. Crypt of the Necrodancer. It's really fun. I really like the idea behind it. I'm just also not the biggest fan of roguelites, because I don't know, it's just, it gets to me that, you know, it gets to me that every time you die, you just have to start all the way over, and it's different every time. But that's, you know, the definition of a roguelite. So maybe I just don't like roguelites. But it's not like I don't have fun while playing them. But I really do like the idea of it, and it is fun while I do play it. Did you just pick it up, or are you thinking about getting it? Because I suggest getting it if that's something you're into. Yeah. You're just thinking about the soundtrack? Yeah, it's a really good soundtrack. It's a very good soundtrack. No, that's not what I wanted. Hey, Do. What's going on? Welcome on in. We're just waiting for a few more people to pop in, and then we can get things started. You have sound alerts based on bits, but you could make them based on error messages. You can? Interesting. How's everyone? I mean, I'm doing pretty well. Not doing too bad. I got some... Oh, can you? I don't know. I don't think so. Probably just gonna alert because you got some reading. Yeah, I feel that. What are you reading? But yeah, I'm feeling pretty good. I spent basically all day kind of like finishing learning how to Git and GitHub. well, maybe not finished, but up to a point where I can do things. And then I got, I think, the last bits on this project we're going to look at done. And so, you know, ready to be presented. And yeah, so yesterday was a really good day. I got a lot of good work done. Oh, we're waiting? Let's add a readme. Twitch code. You know what? Never mind. So the linear algebra chapter in that quantum computing book. Oh, Nielsen and Chuang? This is a very interesting song. What do we can't read? Then I think learning linear algebra might not be your biggest problem. Okay, fam. How about we get into it? Because I don't just want to keep sitting here. So, emergency and dough. Let's look at you are the audience today. But yeah. So, and then we can probably go over this stuff again if more people come in and have questions. Yeah, I figure so. But anyways, so yeah, the GitHub is set up. That's what we're looking at now. You can go here to, I don't know if you saw, we now have a code command. You can go here to the, this is kind of the repository where I'll be putting all of the code and not explicitly not notebooks, but all the code that I make and talk about on stream. And there will be like different folders for different projects. And so like the one we'll be going over today is the Taylor Path project. And so you can just go in here and say, okay, well, I want the code to follow along or play around with. And so you can just click the file itself and you can see all of the code right here. And so you can download that and then modify it, edit it, play around with it, follow along in explanations. The beauty of having the code in this format, in this kind of format, instead of, because this is not a notebook file. This is not a Mathematica notebook file. This is a Wolfram language package. And so the reason why I decided to do it that way is because when you save that package, which you can edit and manipulate and write in Mathematica, this is what it is under the hood. This is what gets saved, this kind of plain text file here. And so, and that's different from Mathematica, because if you were to save a notebook and then open it in a text editor, then you get a lot of metadata and things that you just don't see when you're looking at it in the actual notebook environment. And so doing it this way, I can put it on GitHub. It's a lot easier to actually work with Git. And it's human readable, just, you know, looking at it here online. And it also not being a notebook, like part of the metadata of a notebook is like the position on the screen and then the times the cells were changed and things like that. And so just doing it this way is makes the user experience a lot more like consistent across whoever actually wants to download and use this code. But yeah, and so, but that being said, having it in this format, one second. Darn, I had a sneeze and then I lost it. Anyways, one of the things about kind of publishing code in this format is that there are a few steps that you have to do on or the user has to do on their end in order to use the code. And so, which we will get into. But yeah, so here's the code, and you can look at it right online, and it's very human readable, which I really like. And another plus about putting the code out there in this format, in this package format, in the Wolfram language package format. Hope I find my sneeze again, yeah. I lost my thought. It'll probably come back. I know I put it up in the Discord. Oh, yeah. Another plus about writing the code this way is that, I mean, what we're looking at now is just a simple text editor. And so you can also you can download the file and then open it up in like Notepad or Atom or any other just text editor. And this is exactly what you see, and so you can play around and look at the code even if you don't have Mathematica on hand to kind of load this code and then run it and do stuff. Why you would want to do that, I don't know, but I wanted to make it an option. Yeah, and then, yeah, they're just kind of, it's more of a, I think in a sentence, it's publishing code in the package format allows for a better integration into the ecosystem, into your coding ecosystem. And so that's why I did it. But yeah, and so, yeah, so this is the code. You can go here and download it if you want to follow along, or later, or whatever. Of course, since this is GitHub, you can download the code, and yeah, you can download the code through like Git and edit it yourself, and then, you know, if you see something in here that is like, hey, you know what, this can be better, then you can, you know, download it. Oh, God. You can download it and edit it and then say, hey, non-dairy neutrino, I think this could be done better, and here's my version of it. And then you can submit a pull request, and then I'll take a look at it and say, yeah, you're right. And then I will merge it into the code itself. But anyways, yeah, so this is kind of small for you guys. There we go. But yeah, so anyways, why don't we get into the mathematics of it all? So why don't we go over here, and then, look, we're back in Mathematica. Ah, home safe and sound. Okay, so over here on the left is the code we were just looking at. Same exact code, I haven't changed it at all. And so this is our Taylor path package, because today we're going to be looking at the path that's traced out by the complex Taylor series. And so what we can do, well, yeah, not what we can do. But yeah, so that's what we are calling our package. And then, yeah, you checked it out. Nice. But yeah, so in our package, we can kind of go through here, and then I don't think I'm going to explain the details of how packaging works. You can't edit Mathematica yet, though. Right. Well, I mean, the beauty of this, like I just said, the Wolfram language package, is that you don't need Mathematica to edit this code. You can just use a text editor. You can't run it, but you can edit it if you know what you're doing. There's the Wolfram Cloud, yeah. I mean, I used it once just to try it out, but and that was like years ago. So maybe it's changed, maybe it's gotten better, but I did not like it when I used it. You don't know what you're doing. Yeah, well, I guess that's why you're here, right? To learn. Yeah, anyways. So yeah, I don't think I'll go into the details of what goes into making a package, but we can kind of go through in just words. So the idea, so let's go over here. Let's look at this picture. So this picture was kind of the inspiring incident. Well, me seeing this picture was so inspiring that it was the inciting incident into kind of my compulsion to make a version of this that you can give it any function, not just the exponential function, and any complex argument. And then it will give you these arrows that trace out a path to that, to the image of that value under that function. So emergency, you say, it has a tendency to take a while before running code, but other than that, it works. Yeah, I guess that's fair. But yeah, so kind of recreating this image right here, this plot. It's not really a plot. Well, anyways, not to get into the semantics of it, but yeah. So the goal of this project was to recreate this image, but generalizing it as well. And so, kind of the first thing we need to do is kind of look at this image and analyze and distill the math that's underneath it. Because I think once we have, a good handle on the math and the concepts that are actually going into this, it's much easier to translate that into code. And so what we can do is say, okay, well, our first vector is from 0 to 1. So in this picture, we're considering the, one second. Oh god, I clicked it. I don't know why, but for some reason, my version of Mathematica, if you click on, say, for example, this image, then it loads in a toolbar that will show up, and it just like completely stalls the system, well, the Mathematica session, and you can't do anything until it does this thing and, draws the box and then loads in this toolbar down here. And I have no idea why it does that, but it's really annoying. And I always forget to not click on it. To not click the image. But anyways. Yeah. So if we look at this picture and we say, okay, the So we know that this is kind of a visualization of terms in the complex Taylor series. And so, like, okay, this term down here corresponds to 1. So, like, the 0th order term, or what am I trying to say here? Yeah, the 0th order term in the Taylor series. And then I is the second term. And then I squared over 2 is the third, I cubed over 6, and so on. And so, okay, so each of these vectors corresponds to a specific, the kth vector in this image corresponds to the kth term in the series, in the Taylor series. Okay, and so that means, so if we consider, okay, but now we, tripping over my words here. Since each of these vectors corresponds to a single term, then the sum of these vectors, so like this point right here, corresponds to the partial sum up to n, say, of the Taylor series. So, okay, n equals 1 for this first term, and then n equals 0 for this first vector, and then n equals 1, and then n equals 2, and then n equals 3. And so, so now we have that. But then we don't actually want to visualize the value of the partial sum itself. We want to, because that would be the n equals 1 partial sum would be from the vector going from 0 to I plus 1, or 1 plus I. But we don't want that vector. We want the vector that goes from 0 to 1, and then from 1 to 1 plus I. And so, and so we kind of need to partition our arrows, partition our partial sums to get kind of, okay, we go from here to here, and then we go from 0 to 1, and then from 1 to 1 plus I, and then from 1 plus I to 1 plus I plus I squared over 2, and so on. And so that's kind of the steps that we need to work up to in order to draw our path, to trace the path that is formed from the sequence of partial sums of the complex Taylor series. And so, that's kind of how we start. And so, now if we go over here to the left, we can see, we can kind of come down here and where we define our, define in words what our functions are going to do. So we're going to start with the Taylor sequence function. And so this is the, well, so given a function f, a complex point z, and a number of terms n, the Taylor sequence of the list of those three variables, or those three objects, gives the sequence of partial sums up to n of the Maclaurin series of f evaluated at the complex number z. And so I do call it Taylor path and Taylor sequence and things like that, but we're actually working with the Maclaurin series here. So all of our derivatives are evaluated at 0. That was just calling it the Taylor X. I just started that way, and then I guess just kept it. Even though it may be a little more inaccurate. I mean, of course, though, the Maclaurin series is a special case of the Taylor series, so it's not completely wrong. But yeah, so we can think about it like that. We can think about it kind of up to n, the partial sum up to n, or the sequence of partial sums up to n. But what if we don't know? What if we don't want to stipulate, okay, how many terms we want to go out to? What if we just wanted to go until the partial sum is within some distance, some tolerance of the actual value of the function? Well, we can do that too. And so if we kind of think of the maximum number of terms being infinite, then we have the second definition, where if we say, okay, I want the sequence of partial sums of the Taylor series, or of the Maclaurin series, of f at z, but up to, so yeah, given all of those parameters, this function will give you the sequence of partial sums of the Maclaurin series of f, evaluated at the complex number z to within a tolerance of epsilon. And so that's a nice way that we can just kind of say, and then, well, what am I trying to say? I mean, it's just a way that we don't have to tell it exactly how many terms we want. It just kind of goes until it's close enough. Okay, so now we have our sequence of partial sums kind of in our heads. And so now that we have the sequence of partial sums, so like if we want to go out to n equals 2, okay, so then we have our n equals 1 sum, and then we have our n equals 0 sum, which is just the vector 0 to 1, and then our n equals 1 sum is the vector from 0 to 1, and the vector from 1 to 1 plus I. And then we have another vector from 0 to 1, and then a vector from 1 to 1 plus I, and then a vector from 1 plus I to 1 plus I squared over 2. And so now we have our sequence of partial sums. Great, awesome. So it's a list of vectors. So gives the sequence of partial sums. It's a list of vectors. So Taylor sequence will give you the yes it will, yeah. Oh, interesting. Yeah, I forgot to put that in the definition. Okay, well, we can just add that. So yes, emergency, you're right. It is Taylor sequence will give you a list of vectors, because it gives a sequence of partial sums up to n of the Maclaurin series of the real and imaginary parts of the Maclaurin series of f evaluated at a complex number z. And so now we say, okay, partial sums of the real and imaginary parts of the Maclaurin series of f. Yeah. There we go. Yes. Good catch. Yeah, so this function will give a list of vectors, and each of those vectors is the real and imaginary part of the partial sum up to that point. Yeah. So now we can save that. But yeah, okay, so basically now we have our sequence of points here on this kind of image here. And so now we're at the easy part. That's pretty much the hardest part of this. And so, okay, well then, now we want our path. And so, but like I said before, we don't want a sequence of vectors going from 0 to 1, and then 0 to 1 plus I, and then 0 to 1 plus I squared over 2. we want the sequence of vectors going from 0 to 1 and 1 to I and da 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 da, or 1 plus I. And so basically we just need to kind of partition our sequence in pairs with an offset of 1 to be specific. But if we just want the path, then we can say, okay, given a function f, a complex number z, and a number of terms n, then Taylor path of those parameters gives the list of pairs of points, is the list of pairs of points that trace out the path defined by the Maclaurin series up to n terms of f at z. Now that's kind of a lot of words, but I think in reading it, instead of just me telling it to you, it makes a lot more sense. Welcome on in, Jax. Hello, hello. I'm glad you could make it to this one. I'm actually streaming at a reasonable hour. I figure that might allow for more people to come on in. But anyways, so... Oh, God, I'm so sorry. Bumped my mic. Finally took down the... Yeah. What am I saying here? Yeah, and so, just like before, given the same... It's the same kind of theme when we're thinking about the path that our Taylor series traces out. It's the same theme as the sequence of partial sums, Taylor sequence. And so we can either tell it, okay, go out to this many terms, n, or go until we are within epsilon of the actual point. And yeah, and so... And then we can... And then so these two functions down here kind of are artifacts of trying to be computationally efficient, algorithmically efficient, when it comes to actually running the code. And so basically the path to terms function, well, given a path, say the output of Taylor path to terms of that path gives the list of the terms of the Maclaurin series that traces out that path. Gives the list of terms of the real and imaginary parts of the Maclaurin series. Or wait, no. No, that is incorrect. That is not what I want. I do specifically want the terms in the Taylor series, not the real and imaginary parts. Because we are going to use those terms to label the vectors. And so basically these terms here, 1 and I squared over 2. And so given this path, we get a list of these terms that we will use to label the whole deal. Oh, I did it again. Okay, well, now we have to wait. Okay, no, we're fine. But yeah, and then for each of those labels, we now kind of think about, okay, well, where do we want to put those labels? And so we make a function, label position, and so given a path, we get a list of positions that yield a list of pairs of positions. A list of pairs of positions. Well... Can I disable the image thing through settings? I mean, probably. I just have never done it because it's never been a problem until I actually started this project. Because I think what it is that, well, unless we say import, don't import it as a Don't import it as an image, import it as a graphic? I don't know. Let's look at the import documentation. And then the import documentation. And we go to details, and we say, okay, not elements, not rules, options, data, raw data, image, graphics. That's what I thought. Oh, but yeah. Yeah, so we say, don't import it as an image, import it as a graphic. And now if we click it, then it doesn't do it. Good job, chat. Because what was happening is that when I clicked it, Mathematica says, oh, you're trying to interact with a picture, an image, which is different than a graphic, at least to Mathematica. And so it said, oh, you're trying to interact with this via the front end. And so, okay, well, we've put a lot of work and time and effort and money into developing a toolbar and kind of a graphical user interface to, well, interact with images. And so we're going to pop that up for you. But that actually takes a long time, as we've been seeing. But it doesn't do that with graphics, which is why it's never been a problem for me, because I never deal with images. I always deal with graphics. But yeah, good thinking, chat. But yeah, anyways, it's beautiful. I can just click it and click off and then click over here. You know, it's the little things in life. But anyways, but yeah, so now we have kind of an understanding of what needs to go into the math of this picture here. And so now that we have a good grasp on the math, we can actually start to code. So then we come over to our code and we say, actually, you know what? We're going to come over here. Oh, wait, no, never mind. I have to do that elsewhere. Never mind. Okay. Okay, and so, Jax, if you haven't seen, you can go ahead and pick up this code on the left here at the new GitHub. It will look like this. Well, what that link goes to is this. And then you can say, we are working on the Taylor path folder in this repository. We do have a GitHub. So you can go in there and then you can say, okay, well, I want the Taylor path Wolfram language package. And so you can just click that and then see all the code right here. And so this is exactly what we're going to be working with. Anyways. I mean, I've never used GitHub before I've been trying to do this either. And so it took, I used Git. I tried out using Git for just a little bit. But I just figured that it didn't really, I didn't need it. And so I stopped using it. Easy enough. But now I thought, since I'm kind of trying to publish code and things like that, then GitHub would be the place to do it. And then especially if people want to collaborate and add their own things into it. Okay, so is there a way I can screw it up entirely? I just don't know what to do. I'd really not mess anything up. Nope. You just download the code and then that's it. So you can download the code. So if you're here, if you get to this page, then you can say, Open this file in desktop, run this file, data, data, data. You can, I'm actually not sure exactly, well, I mean, you can just copy all of this and then put it into a text file, actually. But you don't really need to do that. You can go up here and say, no, not add file. It's not like a Google Drive file where I could delete everything. No. No. Because I also have a copy of everything on here on my local computer. The beauty of Git. Am I just being... I mean, I just haven't run into it yet. Interesting. Well, I mean, that's just like not how GitHub works. That's not how it's meant to be used. But anyways, that's interesting. Anyways, but yeah, so there's the code. And so now if we come back over here, okay, let's get started on actually coding our code. Let's code the picture. So I'm actually going to maybe put that over there, and then let's widen this out. Okay, so now, how does that look to you guys? Because what I see in OBS is, it doesn't look great. Is it too small? Is it really grainy and like sharp? Or rather not sharp? Too sharp? Everything's fine. Cool. Can't I line wrap? I mean, I hadn't thought about it. I don't think so, though. I mean, that's kind of one of the... it's an artifact of using this package format. Or, well, in terms of Mathematica, using the code format type of cell. Actually, I remember now, I just read a thing yesterday saying, yeah, you can't code, or you can't line wrap in code cells. But anyways, but yeah, cool. So, for our Taylor sequence, we wanted to take in a function f, and so just as a regular variable, and the reason why this is actually a list of arguments is because of reasons that will become apparent later. It should be in format line wrap. Word wrapping. I mean, yeah, but the thing is with these packages, they need to have certain properties, or rather, they won't work with certain properties. And so, like yesterday, I actually ran into a big issue of... Not a big issue. I just made the mistake of not knowing... Or, well, not knowing something isn't a mistake. I didn't know that you could not include stylized letters in say your package. And so initially I had italicized all of my variables, fzn, fc infinity epsilon, fz infinity epsilon, data data data. And so when I tried to save that, you can't, turns out. Because under the hood, what Mathematica is doing is it's creating like different boxes is the technical side of it, but for these package formats and these code cell formats, it just can't include that type of stuff. Or rather, when you save this file as a Wolfram language package, it reduces down to plain text, and so it doesn't work. And I think word wrapping is also one of those things that these what am I trying to say? These formats don't like. Just visual, I assume it shouldn't break it. Yeah. I'm curious though, does a regular notebook have it? Word wrap, or wrap at window width. Since the notebook defaults to word wrapping and the package does not default to it, I'm going to guess that it doesn't like word wrapping, and so I'm not going to do it. And it's my stream, so I can make those decisions. Could I test it? I mean, sure. Yeah, it doesn't. Like that. Yeah, it just goes off the screen. That's funny. Paper width? Yeah. Yeah, it really doesn't like that. Well, anyways. There. Are you happy now? I'm just kidding. But anyways. So, we want the sequence of partial sums. And so, we give it a function, and then, okay, well, we want to evaluate it. We want to look at this point. Fine. Yeah. And so, but so every point we want to give it, we want to make sure that whatever we give it is not like a word, a string, or something else, or a vector. We don't want it to be a vector. We want it to be a complex number. And so we can do that by using the condition here to say, okay, give it a complex, we can give it a number z, but make sure that z is in the complexes. And so whatever you give it, Mathematica will check, okay, is z in the complexes? And it'll say yes or no. And if it's yes, then you're fine. And if it doesn't, if z is not in the complexes, then you can't, or then it won't evaluate at all. And similarly, we say, okay, for this definition of the function, we're telling it to go out to however many terms. And so we want to make sure that term is a natural number, greater than 0. And so we say, oh, okay, well, let's make sure on the condition the max terms is an integer and it's greater than 0, greater than, oh, I guess greater than or equal to 0. Right, because max terms isn't really the number of terms, but the index that it goes out to, that the sum goes out to. Whoa. Okay. Here we go. So Emergency has redeemed voice act for my choice. Okay. And it looks like we got some B-movie script. Okay, so it's my choice. I think it'll go with the classic. Come on. Okay. According to all known laws of aviation, there is no way that a bee should be able to fly. Its wings are too small to get its fat little body off the ground. The bee, of course, flies anyway, because bees don't care what humans think is impossible. Intro to Barry. Interior. Benson House. Day. Angle. On. Sneakers on the ground. Camera pans up to reveal Barry Benson's bedroom angle on. Angle on. Barry's hand, flipping through different sweaters in his closet. Barry, yellow, black, yellow, black, yellow, black. There you go. Was that worth it? Yeah, Jax. Save up your channel points and you too can make me voice act something. Perfect. Awesome. Yeah, no, keep them coming. I love doing those. Anyways, back to code. Gotta get it's like the voice acting is like the only creative thing that I'm actually like into. Improv comedy is also another one. Like things that I like doing. But yeah. Okay. So, we've told Mathematica what we want to give it and the stipulations on those terms. And so now, thankfully, Mathematica has the native function, series coefficient, that just gives us the coefficient on that. If we say in this form, it gives us the nth coefficient of the Maclaurin series of f. Of x. Well, of f. And so then, since this is just the coefficient, we also need to include our power over here. So we have x to the n. So this whole term right here, this product, gives us the nth term in our Taylor series. And so, because of how series coefficient works, we say, okay, evaluate that, and then kind of replace x with z, and then down here we actually have some code saying, basically what this is doing is that, what am I doing? Why am I saying all of these things and not showing you? Chat is so in the way. Maybe I put it at the bottom. I don't know. But anyways. So, yeah, why am I saying all of these things? This is an explanatory thing. So, if we can sit, you can't see that at all. Let's go. That checks out. There we go. So if we say, okay, we want, say, give us, we're considering the exponential function. And then, so series coefficient can actually take a symbolic n. And so we can just say, okay, well, and we can say, I think this works. N is an integer. Integers, and n is greater than 0. Well, greater than or equal to 0. And so then, hey, Physics OH, what is going on? Welcome on in. Hope you are looking to learn some Mathematica and talk about the paths of complex Taylor series. Actually, we're gonna get a shout out for Physics OH. Boom, look at that, I'm a real streamer. And so if we look over here, what if I went like that? There, you can see that just fine. What am I doing? Yeah, and so kind of what this is giving us is the term in the Taylor series, or the Maclaurin series, of whatever function we give it at the nth term in that Taylor series. And so if we kind of keep going, well, let's just go all the way over here. Checks, yeah. How dare you be so supportive, Eric? But yeah, and so now we can kind of go step by step, and I can actually show you guys kind of the algorithm and steps behind all of these. Instead of just saying it with words, because we have that ability. Anyways, so the first step in getting our sequence of partial sums is to get the terms of the series, so we can add all of them up to different amounts, up to different n, and then kind of just look at all of them. But yeah, and so this is a general expression for the nth term in our Maclaurin series, and then say, okay, well, we want to evaluate it specifically at the complex number z. That, of course, doesn't do anything. I don't know why. And so, okay. And the reason why I don't just have z in here, well, this would work here. It works just fine. We get the same thing. Well, we get the same thing because this isn't doing anything. The reason why I don't include z here is because we want over here in our actual implementation, our series coefficient kind of, it identifies the variable that x is a Oh, right. Yeah, okay. No, we're good. We're good, fam. Thanks, Eric. I appreciate it. I didn't make this playlist. This is actually the playlist from another streamer I watch. And because I can, I'll just give a shout out to them. Shout out Doug. Not scientific. Oh no, not a science streamer. Like a regular gaming streamer. Well, maybe not regular. He does some fun stuff that I enjoy. But anyways, okay. So the reason why I don't put z, I don't just immediately put z in here, is because when we give our function z it's explicitly a number. And so basically that would be saying, okay, so we give it z, and let's say I. And so series coefficient says, okay, if I was to make this z here and z over here, then it would say, okay, f of I is not a function, f of I is a number. And so similarly here, it would try to say, okay, the variable I, but the complex number I, that doesn't make any sense. That's not how that works. And so we need to first evaluate our series coefficient symbolically for an arbitrary argument of variable x. And so after it evaluates that, then we can replace x in that with our specified complex number z in which we're interested. And so that's why we don't immediately put x or z in there. It's because, I guess, in a sentence, order of operations type of thing, and you just, yeah, order of operations kind of, and how things work. I mean, it's like, once you say it, it's like, yeah, duh. But it's like, yeah, that is how things work because of how they work. But anyways, so we first evaluate this symbolically. And so we get an arbitrary term. And then we can state, well, again, I'm saying things, but I could just show you. So if, say, I wanted to evaluate this at I, then it's not going to work because it's saying, okay, let's just, right now we're just focused on this. And so it's saying, okay, I don't know what to do with this because this is not a function, this is a number. And we can see that by, I would say, n. Okay, so like, what's the series coefficient? What's the nth coefficient of the Taylor series of this number? That doesn't make any sense. You don't take a Taylor series of a number with a variable I, one I, the complex number, at 0. So like, that doesn't make any sense, and Mathematica knows that, and so it won't do it. You can't take a derivative of a number. You take derivatives of functions. Or, I'll leave that up. So then we say, okay, let's go back here. So we say, okay, now we have our symbolic term. We have our symbolic term in the series, and then we want to evaluate that at the specific complex number, z, and then, okay, so now we have z to the n, and so we can put I here, and it works just fine. But let's keep it, well, let's work with I, so that way I don't have to keep saying things. Anyways, okay, so now there's that, and then kind of going out in the kind of process here. So also, I should note that this little percent sign is referring to the previous output. And so like, this percent sign is referring to this output, the output of this right here, and then this percent sign is referring to the output of this thing right here. And so then if we, so this percent sign is really meaning all of this, because that's what we've done so far over here. And so what we can do is say, okay, now we can't just, well, so if we, okay, what am I trying to say? Turns out teaching is hard, everybody. So let's say comment that out. And then we say, okay. Okay, well let's put in a... Okay, I want the second term in that series. Okay, it's a half. Well, I want the first term. Okay, it's I. Oh, I want the 0th term. It's 1. But this just gives us each... this just gives us, you know, a single number, but we want all of the numbers. We want a list of terms. And so we can kind of go along and then sum up all of the ones before each index. But we also can't just say, yeah, I know. Well, that's also not what I wanted. So now you may be thinking, okay, well, what would you be thinking? I know what I would be thinking. Okay, but now you're saying, okay, what is this mess of symbols here? So let's just take this and we come down here and we say, okay. So basically this says, so this range from 0 to 2 just gives us a list of integers, 0, 1, 2. And then, yeah, physics OH. I usually also don't know what to think. But emergency says, I thought percent signs were tied to out cells. That is true. So, what we can do is say hold form percent sign and then full form that. And so what this percent sign is actually doing, what it's the shorthand for, is the out function. And so if we go to the out function documentation, we can see, okay, percent %n, or out of n, or a kind of sequence of percent signs, corresponds to the output on the nth output in the session of the system. And so we can say So here, in this kind of context of this notebook, in this documentation notebook, okay, let's expand this, and it does stuff, and then we do some more stuff. But then, okay, you say, okay, well, I want the output on basically line 1. Well, actually, that's not totally correct. I want the first output that was generated in this session. Okay, well, it's this one right here. And then, okay, now I want the second output, and it's right here. And so, but what we can do is have some shorthand and say out -1, because it also takes negative arguments, as defined right here. Out -k gives the kth previous output. And so we can say A. And then we can say do that. And so we evaluate A, and it returns A. It outputs A. And so we say, okay, I want the previous output. Okay, well, that's A. Well, here we go. A, B. There we go. And so what we can do is say, okay, evaluate A, it outputs A. Evaluate B, it outputs B. And now I want the previous output. The output 1 line up. Well, basically. So that gives B. And then, but we can also say, okay, I want to use the shorthand and just say 3% symbols, which corresponds to what this is really saying is out -3. And so it says, okay, well, this is on line 7. And so let's go 1, 2, 3. And so, okay, what is the output corresponding to this evaluation? And it's A. So that's kind of how using the session history or the stack, well, how you can do that in Mathematica. It's very handy. Sometimes when I'm testing functions or like equivalents of different methods, I'll do something like same q applied to out of what is it, negative range, say 1 to 3, and it'll say, well, that's not right. Hello. Okay. Interesting. Oops. Interesting. Anyways. So let's just say, well, let's just take this. Let's delete that cell, and then let's come over here. And we say, okay, that's B and A. And then I would say, okay, well, that's not what I wanted. No. So it's like, that's so weird why it's doing that. I don't know why. That's in standard form. Interesting. Oh, because, yeah. Okay, what is chat saying? Delivery last week. Commands, no food, just package. Cooking stream, made a joke. There you go. But yeah, so when I'm testing like equivalents of different methods, I'll do something like this. I will actually call the long form of out and then give it a list of negative arguments because it's listable, and we can see that with attributes out. So that's a listable attribute. So if you give it a list of things, then it kind of threads over that list. And then same queue tests the syntactic equivalence of things. But anyways, so yeah, that's kind of how out works and percent signs. But so coming back to here, we can say, okay, now we have our list of things, and how replace, or the shorthand version of replace all, works is that, say I have x, well, n rather, and I say one second. Nope, I thought I had found my sneeze from earlier, but it is still lost. Yeah, so basically how replace all works is that you can either give replace all one thing, and you can say, okay, replace in this left-hand expression n to be 1, and then it does it. Or you can say, I want several different expressions, each with having n replaced by 1, and then another expression where n is 2. And so you can do that. And so that's what we're doing here. And so we kind of, this expression right here is exactly giving us the set of replacements that we want to apply to our 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 term here to get multiple, basically to get the terms corresponding to n equals 1, n equals 2, n equals 3. You know, I don't think you really notice until you don't notice how much, like, there is to explain until you have to explain it. If that makes any sense. Because, like, I'm just like reading English. It's like you just look at a word and you know what it means. But if you're like reading a book in English to someone who does not speak English, and then you have to just explain each word as you go along and how the words tie together. But anyways. But I do like this. I'm doing this for a reason. Because people want to learn. So anyways, now we have our list of replacements. So yeah, this is our list of replacements, and then so we're getting our list of replacements, and then when we apply that, we get a list of the terms evaluated at the different ends, which is exactly this. And so that's what we're doing up to here. So all of this has been for this one chunk of code. And we're not done yet. This is the easy version too. So after that, we say, okay, so these are the terms in the Taylor series. 1, I, negative 1/2. You can't really see that very well. I'm just gonna put it right there. But now, okay, so these are the terms in the Taylor series, but those are scalars, and we don't want scalars. We want elements in the plane. And so, how do we do that? Or really, what is being represented here in the picture is the vectors corresponding to the real and imaginary parts of the terms, or of the Taylor series. And so, we can just say over here, and following along over here, we can say we want the real, so real and imaginary, or basically what this function does, reim, is it takes in a complex number and then gives a list corresponding to the real and imaginary parts. I think simple enough. Yeah, and so as we can see, the real and imaginary parts of 1 are 1 and 0, and the real and imaginary parts of I are 0 and 1. And then the real and imaginary parts of negative 1/2 are negative 1/2 and 0. So yeah, now we have a list of the real and imaginary parts of each term in the Taylor series up to n equals 2. But we don't want the individual terms, we want the partial sums up to each of those terms. And so Mathematica has a very nice function called accumulate. Accumulate. That really does exactly that. And that's what we apply over here. basically what accumulate is doing is it's saying, okay, first element, and then a plus b, and then a plus b plus c. So it kind of it takes a list and then returns a list of equal length, but each element is the sum of each of the elements in the given list up to the index at which you are considering. Again, a lot of words. But I think the visualization here is a good understanding of that wordy sentence. And it's a native function, and it just does it. And so it's very, very nice and does exactly what we need. Okay. So chat, we now have successfully parsed through the first function. The first and easiest function. Well, no, maybe not easiest, but the first one. So using this code for a function f, complex number z, and maximum number of terms n, we now have the sequence of partial sums of the Taylor series, or the Maclaurin series, of that function evaluated at that number for that many terms. And with that, I'm going to take a 30-second break. So, talk amongst yourselves, and let me know in chat if this is way too slow. Alright. I'll be back. Okay, everybody, we are back. Welcome in, Neurovibe. Yeah, I see you're just stopping in, but thanks for showing up. I really do appreciate it. Yeah, no, I'm not just ignoring you. Um, but yeah, thanks for the kind words and encouragement. I really do appreciate it. I hope everyone's having a good time. And yeah, and things are going at least. But yeah, thanks for coming in. And if you're still here and want to check out the code later at your own pace, it is available there at the newly formed GitHub. So yeah, all this code on the left is available there. Okay, so where were we? How are we doing, chat? How's everybody doing? Is this way too slow? Jerry Adams. You know, Neuro. Neuro. While my name is Non-Dairy Neutrino, I am in fact not lactose intolerant. In fact, I love dairy so much. Just made useful code. Oh yeah, I saw that. Accumulate random integer 1 1. Well, that will just give. Well, the random integer part. Well, what's a range of numbers? Well, that would take in. What would. How to derail me in one easy step. Put out code. One, two, three, four, six, seven, eight, nine. Hey, look at that. I mean, yeah, because this this is just outputting 1. Or yeah, it's just outputting however many ones. 1. You can also do that. Say, well, let's comment on that. You can also create a kind of an array of just one number using constant array. And we say a constant array of 1 for 10 things. Or you can give it a multi-dimensional thing, and so you want 10 pairs of just 1. And so you can go like that. Or another way you could do the same thing is say 1, but make that constant a function. And so then you can say, okay, I want a 10 by 2 array of 1s. And that doesn't even work with just numbers. You can say, okay, I want the function, the constant function that puts out A to be applied to B. Guess what it gives? A. You don't see this application come up too often, but it's there. It's there and you can use it. Anyways. Oh yeah. I'm not being so Neuro says, Wait, I'm not mean. I swear, lactase is just a way to make dairy digestible for lactose intolerant individuals. It's an enzyme. Just divide 1, or just divide by 1 and add 0. Sure. Okay. Anyways. Yeah. Okay, so. Where were we? I believe we were looking... We have now finished the Taylor series, the sequence of partial sums of what we're talking about. I'm not going to say it again. We finished our sequence of partial sums when we give it when we specifically stipulate the number of terms we want. And that's the easy version. The more interesting version is when we don't give it the number of terms we want and say, hey, just go until what am I saying? Just go until we're close enough, or we're within some distance. Emergency. Ooh, can we simulate enzyme production on stream? Maybe? But anyways, yeah. So. Okay, so what we were just doing is a very functional way and a very Mathematica way of kind of all right, thanks for stopping in, Neuro. Hope you enjoyed what you saw, and if you, yeah, the code is on the GitHub. I don't know if you saw it, so I'll put it out there again. The code is on the GitHub if you want to play around with it later. And yeah, thanks for stopping in. But anyways, so the way we just did is a very oh, thank you. Thanks, Neuro. So yeah, what we just did is a very Mathematica way of implementing this procedure. But when we don't give it the exact number of terms we want, things become a lot more procedural, which may be good news to the coders out there. Emergency says, make a function that takes a genetic sequence and outputs the protein it folds into. I'm lost. I would need to do some heavy research. I think in my computational physics course, one of the kind of options for a final project was protein folding. And I think it's in the book, so maybe? That kind of thing. The way that course is run and the way the book is written is much more geared towards like Python. Not that you couldn't do it in Mathematica. I'm pretty sure Mathematica can do everything Python can do. That'd be interesting, though. That would be interesting, yeah. Okay. So, onto the procedural notion, or the procedural portion of our in-flight lesson. So, basically, for anything you could, yeah. I mute a lot during these streams. Anyways. I lost my train of thought. So anyways, okay. So now we're moving on to this block of code. And so, okay, Jack says, oof, almost midnight. Yeah, go to bed. Yeah, thanks, Jax. I will talk to you tomorrow over on Physics OH's stream. Yeah, good night, Jax. Anyways. Yeah, okay, so if we want our sequence of partial sums, but we don't want to we don't know exactly how many terms we want to go until we're close enough, basically, then we can start with a block, localize some variables, max terms, part sum sequence, or partial sum sequence, the partial sum itself, and then the error function. And then so the error function will take n, kind of the number of terms that the partial sum goes out to, and then it says, okay, what is the distance under the Euclidean metric of the partial sum that on each application we're adding the nth coefficient, or the real and imaginary part of the coefficient. And so basically this is saying this part right here is taking our already known partial sum up to n minus 1 and then just adding the nth term, where each term is the real and imaginary part of the kind of complex number. And then, but then we're also, since we want a sequence of partial sums, we want to append that partial sum up to n to the sequence of partial sum, part sum sec. But then we also want to return the partial sum itself. And so how close is that partial sum to the vector, the actual value of f of z? And so I think, yeah, since we already went over in quite depth exactly what this is kind of going into, I think the rest of it kind of falls out, because we also want to keep things moving. But anyways, so that's kind of our error function. And so, okay, so that's our error function. And so we say, okay, while the error out to some, so if we initialize max terms at 0, and so, okay, if the error is, or the error at n terms is greater than our tolerance, then, okay, increase the number of terms we go out to. And then so it keeps doing that with our max terms plus plus. It keeps increasing the number of terms we go out to until we get within a tolerance of epsilon. And then it returns the exact sequence of those partial sums. And so there we go. Then that's version. There was a point to the first part to make the second part easier. Which I'm sensing a theme is kind of how I do things. But anyways. Okay, so now we actually have our sequence of partial sums coded. But now we don't want the sequence of partial sums, we want the path that's traced out by that sequence of partial sums. And so basically what that means is that we'll come back to this whole big mess in a second. So now we define our Taylor path function. I just noticed that stream elements saying Discord's a pretty cool place does not include the Discord link. Granted, it is down below. But anyways, so where are we? So yeah, ignoring all this junk for 1 second. So our Taylor path function takes the sequence of partial sums of our Taylor series and then prepends the origin to that sequence. And then it kind of partitions that list into the pairs. And so basically what this means, what this does is, let's get rid of all that. And so basically what this does is, if we actually run that, then we say, okay, we want a sequence of partial sums for the exponential function. This needs to be a list. At I, and let's just say for no max, but within a tolerance of, well, actually, something I skipped over was that this piece of code right here is saying that you can, so you need to give the Taylor sequence fz and some number of terms. That number of terms can be finite or infinite, and you can say how close you want it to get, or you can not stipulate it and it will just automatically go to within a tolerance of 0.05. And so what we can do down here is say, okay, I want the Taylor sequence to within a tolerance of 0.05. Which in reality is very big, but in terms of looking at vectors, it's close enough. They're looking at, graphical representations of vectors, visualizing this. 0.05 is plenty close. And so there we go. Now we have our sequence of partial sums. But if we come back down here, so this is what we're looking at right now. Can I make the pretty graphic? You mean this picture up here? We're getting there. That comes at the end. But yeah, so okay, we have our sequence, but we want to start at the origin, and so we take that and then prepend that list with the other list 0, 0. And then the partition function comes in and we say, okay, we want to partition, we want to group the previous list, this guy, into groups of 2. But if we just do that, then it will say, okay, then we have 0, 1, or 0, 0. We have basically a line segment going from the origin to the point 1, 0, and then a line segment going from 1, 1 to 1/2 1. But that's not exactly what we want. So we have this first one from a line from the origin to 1, 1, or to 1, 0. And then we have this next line over here, the point from 1, 1 to 1/2 1. But we don't want that. We're missing this line over here. So what we can do is give partition a third argument, which tells it how much to offset each partition. And so now we have the line segment going from the origin to 1, 0, and then the line segment going from 1, 0 to 1, 1, and then from 1, 1 to 1/2 1, and then from 1/2 1 to 1/2 5/6. And so this is the path. This right here is the sequence of line segments that compose the path traced out by the Taylor series. And so, and then so we're basically done. But so this whole big amount of code right here is basically saying that these are the forms of the arguments for the two different stipulations of Taylor's sequence. And so like here's the first one with the explicitly given number of terms that we want. And here's the one over here that is defined for the second version. And so we can use the pattern capability. Well, we can more not ignore. We can actually talk about the pattern capability of Mathematica and how it actually uses that in functions. And so basically, consider a form that looks like either of these, and then call that form args. And then, so like, does that make sense? That's kind of a tricky one to get into, and it really has to do with just the underlying pattern matching notions within Mathematica. I'm getting hungry, fam. But anyways, if you have questions on that, we can go over it, but I'm not going to spend too much time on it. But anyways, basically, you just ate. I'm sure it was hot dogs and macaroni, right? Definitely not another, what was it? Chicken sausage and some really good stuff. Oh, welcome in. Add them all together. About to go to bed. Yeah, I feel that. I'm pretty much always ready to go to bed. Just eat with one hand and sign language with the other. Yeah. Ooh, Impossible Burgers. I've only had the Impossible Burger once. And it was really good. Like, I could tell it wasn't meat, but only slightly. And that being said, it was a lot more filling than a beef burger, which I was very surprised by. And it was really good too. So I am definitely a proponent of Impossible Burgers. Or maybe it was the Beyond. I'm not sure. Yeah, I'm not sure. But yeah, I highly suggest those. They're very good. But yeah. So okay. So now we have our path. So now we can create this image, but we don't just, well, so we can create this image. So let's create the image. Let's look at something. Let's have some fun. And so what we can do is say, so this package has been ran. But to show you how it would look on your end, what am I saying? So if you were to go to the GitHub and download this code, we'll copy and paste this code into your own thing, then you would have this file, and then you would put this file somewhere, and then you would take this line of code, and use this function get. It basically loads this package. And so we can run that, even though it's already loaded. And now we can say, okay, did it actually load? It didn't output anything. That's fine, because we can say, okay, well, we've defined functions in here. We've defined functions in our package. So let's make sure that Mathematica knows that we can use those functions. And so we can, okay, tell us all of the names that are in the Taylor path package, effectively. And look at that, it does know. It knows there's label position, path to terms, Taylor path, and Taylor sequence. So look at that, it does know. Yeah, so that's nice. What am I saying? What are we doing? We are making the image. We're making the image, but also with okay, so we are, so yeah, let's comment this part out so we know, what am I saying? You can tell I'm hungry. Okay, so we've ran this code that I'm not going to explain because we just want to look at it. And so, oh, well, right now we're considering just e to the I. And so this is what we have so far. This is the path traced out by the Taylor series, the complex Taylor series. Okay, so we're done. Let's go home, right? But this isn't exactly, I mean, like, we can look at it and it's cool, but it's not very illuminating if it's like out of context or whatever. Because as sure, we have the vectors and the arrows, but that it doesn't look like the picture. The picture has these labels. And I think that's actually really important to actually like get something out of the visualization, to actually attach the visualization to some concept. And so we need to, say, create a function to give us a list of these labels, and rather the labels. All right, later, Adam. Thanks for coming in. And oh, I see. You're not later. Okay, thanks for coming in, Emergency. Thanks for hanging out as always. Is it time to go home? But anyways. Oh, you're not actually leaving? Okay. Everybody's still here. But yeah, anyways, so basically, we need to include these labels for this whole thing to actually like mean anything. Sure, we can animate some arrows going along, but that doesn't help us. And so what we can do is we can continue down, and we can say, we can define a path to terms function. And so the reason why, and basically what this is doing is given a path of vectors, or a sequence of line segments type of thing, give us the terms in the Maclaurin series that define that path. And so that's actually pretty easy. So we can say, okay, out of our path. Out of our path. Out of our path. Out of our path. Whoa. So out of our path, we can say, okay, so we can get rid of this. We know how to make a path. We know if I can write path. So this is our path. Even if it doesn't look like it. This is our path. And so now we can say, okay, well, basically we want, okay, let's take a step back. What we're trying to do right now is create the labels for each of these line segments. So like I squared over 2, I cubed over 6, I to the 4 over 24. And so those are the terms in the Maclaurin series up to that point, or whatever. And so this is basically that, or effectively, we've already calculated the terms in the Maclaurin series. And so it's not like through the use of the series coefficient and such. But in order to try to cut down on, like if we give it some weird function or some weird point that it's evaluating at, we don't want to calculate all of these series coefficients again. We don't want to call this function again. And so we can't just take the output and then kind of go backwards a little bit. And so we can say like, well, so from, so each of these kind of points. So what this is saying is out of, go through each one of these pairs and take the second element is what this is saying. And so that is exactly equal to nope. That's exactly equal to our Taylor sequence. Right, and so wow. So basically we can get back to our sequence of partial sums from the path, and then each partial sum is, well, and then each of these, this is the real and imaginary part of the partial sum. And so, okay, well, how do we get from a real and imaginary part back to an actual complex number? We just use the definition, or the, well, isomorphism between the plane and the complexes. And so we can say, go like that. And basically what this is saying is, so we define a function that takes its first argument and adds to it I multiplied by the second argument. And then what this is doing here is saying, basically hop over this whole list, and instead of having these elements 1 0 or 1 1, instead of having them be in a list or passed to the list function, have them be passed to the kind of this function here. And so what we get is, okay, what am I saying? 1 plus I times 0, and then 1 plus I times 1, and then 1/2 plus I times 1, and so on and so forth. Okay. So now this gives us the sequence of terms of the partial sum, or not sequence of terms. This gives us the actual sequence of partial sums, the scalar versions. And so, but we don't want actually that. Okay, well, let's see. Adam says, before I do go to bed, I need to tell y'all, because I'm excited, big science announcement coming tomorrow. Tentative but compelling detection of biomarker chemical phosphine in the atmosphere of Venus. Tentative but compelling detection of biomarker chemical phosphine. As in life? Are you saying, is this is this an exclusive right here? Are we hearing this for the first time? We heard it here first. Conclusive evidence. There is life on Venus. Everybody, you heard it. You heard it here first. Tell your friends. Tell your family. Tell everyone. Shout it from the mountaintops. Conclusively, 100%, without a doubt, we have found life on Venus. That's super cool, Adam. I will be very interested to see that. Thanks for the inside scoop. No, I think what you're saying is that you've been to Venus and you've talked with aliens. I think that's exactly what you're saying. Tell your friends' family, yeah. Aliens, yeah. But yeah, no, that's super cool. Thanks for telling us that. That's awesome. Is it gonna be where is it going to be announced? Is there like a live stream of a press conference? Well, anyways. Okay, so far we have the sequence of partial sums, but we don't actually want the full partial sum at each point. We just want... okay, CosmoQuest is streaming the Nature press conference tomorrow. All right, we'll be sure to check it out. Shout out CosmoQuest. Had to do with the Cali fires. We'll have to see tomorrow. Interesting. Oh. Interesting. I'll drop them a follow so I don't miss that. Oh, that's in French. Interesting. Okay, well, we'll see. So we'll put that there, and then we'll go like that. Okay, so we're going to be... Okay, so now we have the sequence of partial sums up to... So the kth term in this list is the sequence, or is the kth partial sum. But we don't actually want that. We want the individual kth terms in the series, not the kth partial sum. And so what we can do is, since basically so basically the term, the kth term, oh my god. basically, we realize that the kth term of the series is equal to the kth partial sum minus the k minus 1 partial sum. And so what we can do is, so this is our list of partial sums. So basically, we don't want this, we want this minus everything that comes before it. And similarly with each term. And so what we can do is use this differences function. And so we go like that, and then, hey, look at that. And so now we have, well, ignoring this one, we have I, and then I squared, which is -1 over 2, and then we have I over 6, or negative I over 6, and so we're almost there. And so we really just need to, because this differences function is ignoring the first term. It basically starts at the second term. And so we just need to prepend the first element. And so now we actually have our labels. We have the terms in the partial sum. 1, I, -1/2, negative I over 6. We'll put that there. So yeah, that's our path to terms function. So given a path, we can get the terms, the individual terms in the series up to that point. Okay, so now that's going to constitute our labels for each of these line segments, for each of these arrows. But now we want to make sure that all of these labels are actually put in good spots. Oops. And in fact, we can actually add we can add the labels. I'm not going to do that. Okay. There we go. Oh, that's what I did last time. What am I saying? Okay, so we're almost there, chat. So we want to make sure that these labels are always positioned in a good way so we can actually read them, which doesn't actually come out to be that way when you include too many terms. But here we are. I think it's the best way that you can do it. So, to that end, we need to define a function that for each label, well, for a given path, gives us the positions of the labels that are always aesthetically pleasing. And so what we can do is we take our path and then we go like that, and then we go like that. So, okay, so we have our path. And then, so if we come down here and we take the right, okay. Okay, so before we get into that, we need to talk about the rotation transform function. Basically, what this is saying over here is it's saying, Prof. Melko, what? We have some big names coming in here. Welcome in, Prof. Melko. Mod, me. Can we get a shout out? Heisenberg, can we get a shout out for Prof. Melko, please? Oh wait, is that trademarked? Is that patented? But yeah, welcome on in. If you're interested in look, yeah. Well, I can't say they don't know where to find me. But yeah, if you welcome, thanks for coming in. I hope you're interested in seeing some computational math, or, I mean, I don't know if I'd actually call it computational math, but just some fun visualizations and looking at code and things like that. And if you are interested in the code, it is available on the GitHub. And so, yeah. And so if you're interested in looking at the paths traced out by a complex Taylor series, then you are in the right place. And so we're actually nearing the end of our journey here. All right, well, thanks for coming out, Adam, and hope you come back and have some fun. Sleep well. But yeah, so all right, later, Adam. But yeah, so if we consider the rotation transform function, basically what it's saying is, if we make this a function and then we give it what are we saying here? So let's just give it and then so basically what this is saying is take in a vector and then give a function. Okay, so this rotation transform defines a function, and we can actually just look at that and say, yeah, I know. Of course that doesn't do anything, because so basically what this rotation transform function is saying is it's giving a function that takes its input and rotates it by -pi/8 radians around the vector 1, 0. Oh yeah. Chat, why did you never tell me that this notebook was not zoomed in? There we go. Okay. Hopefully that's better. Awesome. Very awesome. Okay. So, basically this function is this function creates a function that rotates its input by -pi/8 around the vector 1, 0. And so we can actually also just say, okay, rotate it around the vector 1, 1, or the point 1, 1. And so now we can say, okay, we want to rotate our 1, 0 vector around 1, 1 by -pi/8. And so then that gives us a vector. That's pretty clever, Melko. Good use of emojis. Horizon Sight emote. Interesting. But yeah. And so, using that kind of functionality, we can come back over here, and so we can define that function. And basically, what we're going to use it for is say, so the vector that we're going to be rotating around is the line segment between each of our points here. And so basically, what we're going to do is say, okay, take this vector from 0 to 1, these points here, and cut it in half. So go to the midpoint of this line segment, and then rotate that vector by pi over 8 to the right of the vector. And so this is always kind of in context. And so since we're doing this relative to each vector, we can just kind of stipulate the pattern, and it just works every time. And so yeah, so we have this function that rotates a given vector around another vector in the plane. And so then we use this thing called MapThread. And MapThread is a very nice one because it takes, say, a function f, and, well, we can say, and then, what am I saying? And then, so, yeah. Wait, what is it not like? Oh. Good job, chat. So basically what MapThread does is it takes whatever function you give it, and it takes, say, like, the first element of this list and the first element of this list, and then it puts that in the first element f of those two elements in the first position of the output list. And so another way to think about this is, say, I think if we take the same list and then we transpose it, so basically if we take this list and then we transpose it to have pairs take this list, transpose it to have pairs AC and BD, then we say, okay, well, instead of this being a list of lists, we want it to be a list of F applied to those those elements. And so that's basically what MapThread is doing. And so the list we give MapThread, in which we want to apply our rotation, is the list of our vectors what am I saying? Yeah, so everything in this list here is going to go in this position over here, which is also very small. There we go. Is that better? That looks good. That looks good. Okay. So basically, we take each, sorry, Milko, do you have a really good mic, or is your voice just that damn buttery? I'm gonna say just a little bit of both. Butter. But yeah, and so basically what we're doing here is for every vector, so for everything in here, it's going to go in here. So this is the list of vectors that we are going to be rotating around. And so basically that's this kind of vector. Right. Yeah, and so basically that's going to be the vector from 0 to 1, and the vector from 1 to 1 plus I, and then the vector from 1 plus I to 1 plus I squared over 2, and so on. And so those are the vectors that we're going to be rotating around, and then the vectors that we are actually rotating are the vectors formed from the midpoint bisection of these line segments of each of these vectors. Well, what should the... I have the link somewhere. I will post it later if that is something people are interested in. I do really like this mic, though. I've very much enjoyed and appreciated its um, its performance since I've gotten it. I really like it. It's pretty cheap too. I got the whole setup, the mic, 2 windscreens, and the boom arm, all for like $80. And so I think it's a really good setup. I'm very happy with it. Can I strap it to a bicycle? Probably not. It does have a windscreen though, so no. Plus, you know, I don't want to end up being like an hour late home to my wife if I had a wife. I'm not a big geocacher anyways. But yeah, so we're rotating a bunch of vectors. We're rotating our bisected vectors around our bigger vectors just a little bit. And so this gives us the list of positions that our labels are going to go, if that makes any sense. Okay. But so, chat, we've reached the end of our package. We've reached the end of our pre-made code, the list of our functions. So let's do something with it. So now we come back over here and we say, okay, we're done with that picture. Let's make our own picture. And we ignore all of that. And now we just come down here. And I think in this moment we are going to ignore most of this kind of just setting up the graphics and say, let's go over here and say, okay, let's run that. And so now we've used all of our functions. We've used our Taylor sequence function to get our sequence of partial sums of the complex Taylor series. And then we apply our Taylor path function to that, well, kind of, to get the path that's traced out by all of these sequence of partial sums. And then we get the labels for each of these line segments, and then we get the aesthetically pleasing positions of those labels. All of this done programmatically and automatically, and so we don't have to actually do anything, at least in my head. And so what does that give us? Well, for an argument, or for the function, the exponential function evaluated at I, the complex unit, we get this nice animation here. And so as you can see, well, let's leave it blank. As you can see, so like on this vector here, it goes from 0 to 1, and then our nice little 1 label here. And then on this other vector, let's pause it. We see that this vector corresponds to the I term in the Maclaurin series. And then this vector over here corresponds to a term of -12. And then this vector down here corresponds to some more stuff, but purely imaginary. And so we did it. We have now successfully, well, effectively recreated this over here. Just so we can zoom in, we can say, we can zoom in on the upper right quadrant and say, starting from left to 1.5, and then from bottom of -0.1 to 1.5. Then we can zoom in and we see a beautiful sequence, the path traced out by the we can see the beautiful sequence of partial sums of the complex Taylor series that trace out the path visualized by these vectors. Good job, chat. You did it. Isn't math a beautiful thing? We can speed it up. But so, what if we don't want the exponential function? Or what if we don't want to just look at I? We don't have to. Because we've done this, we've implemented this so that we can put in any function and any complex number. So what we can do is we can, because this code is written poorly as is, we can scroll back up here and we can say, okay, well, what if we want to look at I pi? E to the I pi, everybody's favorite identity. Now this, of course, will be -1 in the end, but what path does the Taylor sequence, or the Taylor series, trace out in the complex plane as it gets to -1? Well, we can, well, after I undo that, what path does the Taylor sequence, or Taylor series, trace out? And so you can see here that if we don't go that far, so we can actually still see some labels, we can see that, okay, the Taylor series starts out going right, and then it shoots up, and then left, and then down, and then right again, overshooting -1, going back to the right, and then it goes back up, and then left, and then it actually ends up spiraling in to -1. It converges on -1, but it doesn't go there directly. It kind of takes this weird spiraling out and then back in path. And so I think that's something really cool to just see kind of how math behaves, if you will. Yeah, and as you can see here, due to how we've defined the positions of the labels, once the vectors start getting very small and close together, the labels start overlapping. So that's an artifact that maybe I will try to fix in the future, but I think right now, for these other vectors, so like this vertical one corresponds to a term of -pi, or plus pi I think. And then likewise over here, and a nice label over here, and over here. I think it does the job pretty well. Yeah. And so that's, I think, a really cool thing to see. But, so now we can also not just give this kind of angles or terms on the unit circle, but what if we say, what if we want, what is the path the Taylor series traces out when it approximates e to the 1 plus I? And so we run that code, and then we run this, and we say, oh, okay, well, there it is. We no longer have to wonder. It goes out, and up, and then left a little bit, and it's a beautiful thing. And so, since this is manipulatable, we can define however many we want, and things like that. And so, are there any guesses as to actually where this sequence of vectors is converging to? Because it really is just e to the 1 plus I. And so if we consider our rules of exponents, e to the 1 plus I is really, you can split up the sum into e to the 1 times e to the I. And so then we have e to the 1 being our kind of modulus of the complex number, and then e to the I being kind of the direction along the unit circle. And so really, e to the 1 plus I is, of course, e to the I, but just extended, or with a magnitude of e. And so I think if we do some live coding, we can actually see that. And I'm done with that song. Okay, so let's see. All right, live coding time. So if we also include an arrow from 0, 0 to, well, yeah, of args 1 of args 2 oh, it doesn't like that. That's because, so we did that, that's a sequence. Good job, chat. There we go. So now we can see that the path that it's tracing out is actually, well, here, let's make this a nice bright red. We can see that the path that's traced out by this Taylor series algorithm is exactly converging to the, well, I mean, exactly what it should be. But, I mean, here's a nice visual way of showing that. And something else I could add to this is, say, if we say instead of the vector itself, but rather the vector going from 0, from the origin, to the point on the unit circle, kind of giving us a direction, and then doing something to signify the modulus of the number. That could be something, but that's not coming to my mind off the top of my head, and so I don't think we're gonna live code that. But yeah, there it is. But so what if we don't even want the exponential function? What if we say, hey, that's been done, it's a rotation, great. Tell me something I don't know. Okay, well, we don't have to. We can say, okay, let's consider the logarithm of, say, just I. And so then we do that, and it does its thing. And then, look at that. The logarithm of I is just, it's just one term. What about 1 plus I? Oh, that's interesting. It's very interesting. What if we say the logarithm of I pi? Okay, well, something's going on here. I didn't actually test the logarithm, but well, I mean, so what this tells me is that the Taylor series of the log function, so we can actually just say, okay, series of log of x in the variable x at 0, because it's the Maclaurin series, out to, say, 3 terms is just itself. And so there is no Taylor series. There is no sequence of partial sums. It's just itself. Because if we don't evaluate at 0 and we say x naught, then we get some stuff. But if we consider x naught of 0, then or x naught at the origin, then it doesn't make any sense, because we're trying to divide by 0 here, and Mathematica does not like to divide by 0. And so, yeah. And so it just kind of doesn't do anything. So log of I tau. I mean, as we have just shown, it's not going to do anything, because the Taylor series, what a pleb, yeah. It's not going to do anything because there is no Taylor series for, or there's no Maclaurin series for the natural logarithm. as is demonstrated right here. Divide by 0 3 times a day. I mean, you are a particle physicist, so I think that makes sense. You and your infinities and trying not to... If you just squint at it, yeah, sure, the math works out, but like... I mean... Are you sure? Yeah, okay. So what if we don't want log? What if we just want... I don't know. Let's try the square root. What is the square root of I? Oh, it doesn't like that. Here's one for you, chat. Oh, it doesn't like that. What if we say just the square function? Look at that. The Taylor series of that is just itself. Go figure. Well, what if we do, how about, right. Search. Okay, let's see. So they're trying doing the plus of 1. So just addition? Am I understanding you right? Emergency? What's a good function to look at the Taylor series of? How about this one for you? How about e to the negative x squared over 2? How about we get some Gaussians in here? See, there we go. There we go, chat. So now we come up here, and we go like that, and we say that, and then we go like that, and then we say, okay, what is the path traced out by the complex Taylor series of the Gaussian function evaluated at I? Well, look at that. As we can see, if we take out our red arrow here, let's comment that out, and then go like that, and then we redo that, we can see that the actual terms that are being evaluated are strictly on the real line, because the Gaussian evaluated at I is just root e. It's a real number. And so, yeah. Or we can actually look at the Taylor sequence, Taylor with a capital S, sequence of our considered set of arguments here. And we can see that the actual sequence of partial sums of the Taylor series is just, it goes from 1 0 to 1 0 to 3 halves 0, 3 halves 0, da 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 da. And so we can see that the sequence of partial sums is always real, and so the path traced out will just be strictly along the real line. And so there's no going around the complex plane to get back to a real number. It's just always real. probably be because of this square right here. But what if we don't want to evaluate at I? What if we want to evaluate at 1 plus I? Ooh, chat, look at that. Because what we can do is... Well, we may want that. So if we're evaluating at that, and then we can also say go over here and say, okay, the sequence of partial sums does go into the complex plane. And so we can say, okay, it's going, and then it's kind of going out, and then comes back. And so if we actually re-implement our kind of red direct arrow, then we can see that this sequence of, we can see that the Taylor series is converging on this little point right there. Boop. And so, yeah. And so we could sit here all day and play with, you know, different functions and different numbers in the complex plane, but I think this is, I have achieved the goal that I wanted to with this project. So all of this code is freely available on the GitHub. I don't know if everybody here has seen it, but it's there. It looks like this. GitHub code and the Twitch code repository. So I will be putting all of the code and projects that I do on stream here. So it'll be all interactive, and you can follow along as with the stream if you want, or you can just download it and change it and edit it yourself. If you see things that you think could be better, this is GitHub. It's a collaborative platform, and so you are more than welcome to submit pull requests and tell me how it could be better. And so we're working right now in the Taylor Path project folder, and then the code that I've been using, this code over here on the left, is exactly this code here. And so all the code and projects are available online to be used at your leisure. And I think this could be a really cool tool to introduce to help students visualize in, say, a Calc 2 course, or when you're learning about series, or even a complex analysis course for a more advanced student in their mathematical programs, or engineering students would also do it. Gath, welcome on in. Thanks for showing up. Excuse me, Schrodinger, can we get a shout out for Gath, please? Are Heisenberg and Heisenberg accessories all trademarked, Milko? Yeah, thanks for coming in. Yeah, I don't stream very often because, you know, work a full-time job outside of this, and then, yeah, and it you know, there's a lot of work that goes in. I'm sure, you know, I don't have to tell all of you, but there's a lot of work that does go into these things. And so, I usually try to at least do, you know, a Mathematica stream and science at least once a week. Ash, welcome on in. Oh no, it's a lot of math. Well, the beauty of programming is that by its very nature, it's very step by step, and so you don't need to understand and process all of the math at once, but just in baby steps, and by the end, you have the whole thing. So emergency, what's this license? This is a student license. So I can't use it to, well, I'm not sure exactly, but, what am I saying? Yeah. Anyways, so Ash, I'm doing pretty well. How are you doing? This is that Mathematica program, and so we can use this program to visualize things like this over here. The path traced out by the complex Taylor series. Oh yeah, emergency. This Taylor code. It's I don't have it listed on the GitHub right now, but it is going to be under the MIT license, and so, which I believe is just the standard for kind of these open source code projects. And so, yeah, feel free to do with it what you will. Yeah. But yeah, so yeah, again, kind of thinking of the pedagogy that goes into like building and looking at these types of things, I think it could be really helpful for like students to see kind of what's going on bit by bit and step by step and behind the scenes of this like once you get into it, rather like weird machinery of a Taylor series, especially in the complex plane. And so like it's not magic, it's just you take each term and then you kind of go out in bits and just add a term at a time and just see where that takes you in the plane. And so I think this kind of implementation gives a much more intuitive way of understanding a complex Taylor series. For specific functions, of course, you can't really do much with this when talking about the abstracts of it all, but for those that maybe find themselves struggling, I think this could help a lot. Mathgic, yeah, Gath. But yeah, so all of the code to implement this animation, well, I guess I can put this actual graphics implementation in there too, which I will do after stream. But yeah, so all of the code that goes into this, and I'll put the graphic stuff in there too, will be available on the GitHub, and so all you have to do is download it and then have access to a copy of Mathematica, and you too can visualize tracing the complex Taylor series. And I think that's where we're probably going to wrap it up for today, because I'm getting pretty hungry and I'm running out of water. Okay, so Ash, what's this program supposed to do anyway? Because all I see is the vector doing a movement. Well, that's the whole, that is the goal of it. It's just meant to visualize what's going on in the Taylor series. Yeah. And kind of, why I'm streaming this is to show people that want to learn Mathematica and maybe see some cool animations and visualizations. I want to give them the opportunity to achieve their dreams. Taylor series. Yeah. I mean, talking about what a Taylor series is, I mean, other than exactly what you were seeing on screen, I would think that this could be a definition, somewhat, of a Taylor series. But what it actually is a whole can of worms. Yeah. Okay, so is the animation code included in the package? It is not currently. I am going to add that after stream, though, because I think I'm going to wrap it up here. Even though we got some good people in here now, but there will be more streams. But yeah, you know, gotta take care of myself. I'm hungry, thirsty, my throat's starting to hurt. Turns out talking for a few hours straight is, puts some wear and tear. Yeah, Ash. I mean, it just takes time. It just takes time. But yeah. And butter down my voice. For those of you that do appreciate my voice, in the channel points, you will notice that you have the option to make me voice act things. So you give me a statement or a line or something in which to act out in some kind of character. You can't see me, but that's the beauty of voice acting, is that you can form your own mental picture of the character that I present to you via my smooth, buttery voice. But anyways, I think we're gonna wrap it up here. Is there anyone out there to raid? So, like, for example, earlier, Emergency redeemed the beginning of the B-movie script, which I voice acted, and I thought it wasn't too bad. Oh, it's me. Okay, let's see. That's because I'm being hosted by the channel that my browser decides to default to whenever I push T. So let's see. Ooh, voice act. Okay, my choice. Ramble for 1 more hour. How about this? Ramble for 1 more hour. That was a king telling his jester to ramble for 1 more hour. Okay, so who's on? We got Simuleos is on, Laboratory 24 is on, Ty's on. Who we thinking, chat? Yeah, Gath. It's something that I really like to do, and I think I do have a talent for it, and so I like to kind of get into it. It'll be interesting to actually hear what it sounds like. I always review my streams afterwards. But yeah. Okay, chat. Any ideas on who to raid? Dang, requests aren't Turing complete then. Ooh. Oh, physics Tom thinks? I mean, I was thinking about it. He's doing some... What's he doing today? Ooh, painting with Borb. Yeah, I think we rated Tom Thanks the other day. Or no, it was... He was where I landed after, like, some raid train. And I loved it. I think we'll go to Tom. We'll see what he's doing. So the rest of you can be introduced to the art, really, of Tom Thanks. So raid Tom Thanks. Okay, chat. Well, this was fun, and tune in next time to see what we do. I think maybe next week, if I don't think of anything, will be book scraping. Springer released a bunch of their books for free a while back, nearing the beginning of all of this, of our new way of life. And so I developed an algorithm and a process in Mathematica to kind of go and download all of them. And it's a really great resource. And so with this code, I will publish it, and the book scraping code, I will publish it. And so you can also get 8 gigabytes of scientific text. All right. Thanks, everybody. It was fun. Check the GitHub. It will be the new code with the animation stuff in there will be posted later. All right. Thanks for coming out, everybody. Talk to you later. Don't have too much fun.